Well, welcome back. This is pre-section 6.4 where we're using integration tables. Integration tables from the back of your textbook. And if you go to the back of your textbook, and I just actually made a copy of the back of my textbook, you will see, starting on page square 4, the basic integral tables. Now these I have for my students, and I blocked out these guys because you're supposed to have them memorized. But it's starting around formula number 16, 17, 18. These are formulas that basically are what we call CRC hand table formulas. There's a big book, CRC hand tables, that actually has all the integral formulas you ever want to know about any kind of integral. And our textbook has taken probably the best 120 plus formulas and written them out for you guys because and they've done it in a way that kind of mimics what these classic CRC hand tables have. They have forms involving. So what does the form look like? So they've separated by what integrals look like. So these are forms involving the square root of a squared plus u squared. There, if you turn the page over, you'll see forms involving the square root of a squared minus u squared. Down here you guys can see that. Square root of a squared minus u squared. Forms involving the square root of u squared minus a squared. Keep on going. Forms involving a plus bu. Lots of those formulas. Forms involving trigonometric functions. You've got sine squared, cosine squared, all the way up to tangent cube, so forth and so on. Forms involving inverse trig forms. Forms involving exponential logarithms. Forms involving hyperbolic formulas. Forms involving the square root of au plus 2 times au minus u squared, square root of that. So, and again, this is just like the classic CRC hand tables where they have a bunch more formulas and they're all broken into what does the formula that you're trying to integrate look like. Now, the other thing you will notice about these CRC hand table formulas is that they're all based upon u. So the trick of using integral table formulas is honestly u-substitution. The substitution rule is the trick of how to do formulas. So instead of trying to turn it into a formula you have memorized, you're basically going to turn the problem into a formula that you can look up in terms of how to integrate. So let's take a look at the first example that I have for you guys here to show you what's going on here. Now, the trick on this one is we would like to integrate the square root of 25 minus 9x squared. Now, this looks like a number, or a number minus, it looks like something squared. And if you look at your hand tables, you see that there's forms involving the square root of a squared minus u squared. So if I go to my formula, I can even tell you which formula it is in your book. Forms involving a squared minus u squared, because this is a constant minus u squared. So I'm going to flip over here to my forms. So here's forms involving a squared minus u squared, and you identify this as a number minus u squared, so it looks like this formula right here. And I just went ahead and copied the formula out of the book for you guys. So here's my formula number 30. This is formula number 30, and that mimics what this guy looks like. But we want to integrate this square root of 25 minus 9x squared. How do we do that? Is you must identify, and it's u-substitution. So, and actually more like u squared substitution here. Identify what u squared is. The u squared has to be the 9x squared. That also makes the a squared equal to 25. But once you identify u squared, then you need to identify u. Obviously, you take the square root of both sides on this thing. So, taking the square root of both sides, you end up getting u equals 3x. And same idea with a squared equals 25. To figure out a, you take the square root of both sides, and you use a equals 5. And honestly, I know when you take the square root, you always have plus or minus options. We always take the positive option because the formula will tell us when they want us to have the negative. But as I mentioned to you guys before, this is based upon u-substitution. So once you identify u, you do the u-substitution techniques. The next step is to take du. What is the derivative of 3x? It's 3dx. And just like u-substitution, you move the constant to the other side. So 1/3 of du equals dx. Now the goal here is to substitute. And if I substitute it right, it should turn into this formula. Well, this is my a squared minus this was my u squared, but in place of dx, I'm going to put a 1/3 du. But like always, where do constants get to go? In front of my integral. So this is equal to 1/3 the integral of the square root of a squared minus u squared du. Keep the constant out front, and you'll notice that this is exactly this formula. So when you substitute the formula in for the integral, this is 1/3 times u over 2 times the square root of a squared minus u squared plus a squared over 2 sine inverse of u over a. And at the end of the day, they even help us out by putting the big old plus c. So I just recopied my formula, but there's a constant out front here that I have to worry about, and he will distribute through. This particular formula has two terms, but I'm going to put 1/3, and then, like always, back substitute. What was u equal to? U was equal to 3x. So replacing u with 3x, I get 3x over 2 times the square root of a squared gets replaced back with 25. U squared is 9x squared plus a squared is 25 over 2 times the sine inverse of u, which is 3x, over a, which is 5, close bracket, plus c. And there's my solution, and the only other thing I could possibly do to clean this up is remember that 1/3 constant that was out front. You could distribute that and get the cleaned up back of the book version of this thing, which would be x over 2, because the 3's would have canceled, times the square root of 25 minus 9x squared, plus then you have to distribute 1/3 here. So this will be 25 over 6 times the sine inverse of 3x over 5 plus c. So the whole purpose of using table integration is to integrate really hard stuff. So here's a particular formula right here, and I want to integrate this guy. You have to first find, in this case, u squared and a squared to figure out what u and a are, but it's u substitution. Then you have to do du, move the constant over, and then substitute. And once you substitute, it should turn, with the constant out front, turn into a formula that you have looked up. Instead of memorizing the formula, we look up the formula, replace the integral form with its solution, and then we back substitute, and then clean it up for the final solution. So it's has its moments in terms of difficulty because trying to manipulate these equations, but it is really based upon the classic u substitution. So let's take a look at another example. Here's one. We want to integrate, let's just look at the problem first. We want to integrate sine squared of 5x plus 1 dx. Now, even before I even start looking for formulas for this thing, I've got to first identify, well, what format is it going to be taking on? So, again, looking at your CRC hand tables in the back, clearly this is forms involving trig. So I turn to my forms involving trig page, and I see that I have a sine squared here. And being sine squared, it's your first one right here, but you'll notice on my formula they let u equal to the angle. So based upon the fact it was sine squared, I've got to figure out what u is, because this is u substitution. U would be the angle 5x plus 1. Then I need to do du, which is 5 dx. And just like u substitution, move the constant to the side, divide both sides by 5. You get 1/5 du equals dx. So when you substitute, this will be the sine squared of u, and the dx gets replaced with 1/5 du. The 1/5 is a constant, it goes out front, and du goes in the back. And if you look on it, this is a formula number 63, and I went ahead and wrote it up here for you guys, so it made an easy reference here. Here is the formula number 63 out of our book, and it's equal to 1/2 u minus 1/4 sine of 2u plus c. But we have that 1/5 constant up front. Hold the constant out, put a big old bracket there, and then replace the integral with its equivalent formula. 1/2 u minus 1/4 the sine of 2u, and outside one big old plus c. And then, of course, just like with standard u substitution, because this thing doesn't have bounds, I'm going to back substitute 1/5 times 1/2 of u, and we let u be 5x plus 1 minus 1/4 the sine of 2 times u, 2 times 5x plus 1 plus c. And the only other thing I could do to clean this guy up would be distribute my constant. So this would be 1/10 times 5x plus 1. I guess you could distribute the 10 some more if you wanted to. Minus 1/20 times the sine of, and I could distribute this. This will be 10x plus 2 just to make it look good, plus c. And there is my solution. But again, I can't emphasize the importance of understanding the concept of standard u-substitution. And again, with this type of material, that's where most students make their mistake at, is they'll try to figure out what u is. They'll try to plug it into the form immediately. But remember, it's u, du, and you have to move the constant aside, and it shows up in the problem typically out front. So keep up with that constant. Let's do another one. So try this problem here. We want to use the tables to find the integral of 5x squared divided by the square root of 17 minus 9x squared. Well, first off, you'll notice that this is forms involving, and again, it looks like the square root of a squared minus u squared, because it's a constant minus, looks like a variable squared. And again, if you look at your tables in the back of your book, you'll see that forms involving a squared minus u squared, that basically is to get you started. But be careful on that, because in case there's something else that shows up here. So in this one, again, it looks like forms involving the classic a squared minus u squared look. So a squared would be the 17, u squared would be 9x squared. But it's u substitution, so I got to get down to the u level. So I'm going to take the square root of both sides. That makes u equal to 3x, but it's u substitution. So don't forget, take du, the derivative, which is 3 dx, and then move your constant aside. 1/3 du equals dx. Now, the real trick on this stuff is take your formula that you're given and substitute it in before actually going and hunting for these formulas that it's supposed to look like. So this will tell you the integral. This is a division problem. This was the square root of, that was my a squared minus u squared. The dx literally gets plugged into it, and I'll just go ahead and put the 1/3 du because I plan on cleaning it up later. So literally substitution. There's my dx is 1/3 du. 5 is a constant. Constants hold over, but there's an extra x squared on this thing. You do have to manipulate these guys. Remember, we had u squared was equal to 9x squared. I want to substitute in for x squared. That would make x squared equal to u squared divided by 9. So the plugging in for u squared, x squared, which is u squared divided by 9. Now, before I again go to the formulas, I'm going to take this guy and pull out all my constants. This is 5/9 times 1/3. That's going to make it 5 over 9 times 3 is 27. Times integral of, still got u squared on top, pulled out all my constants, divided by the square root of a squared minus u squared du. Now I start looking for my formulas in my tables here. Forms involving a squared minus u squared, so I come up here, but this one was a u squared over. So I'm looking for, looks like formula number 34 here, which is the square root. I'll blow it up, you guys can see this. U squared du over the square root of a squared plus u squared. And that's negative u over 2 times the square root of a squared minus u squared plus a squared over 2 sine inverse of u over a plus c. And you'll notice that when I actually did these notes, I actually went ahead and wrote down the formula that I'm going to need here, so it made it easier for me to plug it in. But keep up with that constant. So this would be equal to 5 over 27 times bracket my formula, which is negative u over 2 times the square root of a squared minus u squared plus a squared over 2 times the sine inverse of u over a. And then a big old plus c at the end here. And then you want to back substitute, negative 5 over 27 times negative u, and u was 3x over 2 times the square root of a squared was 17, minus u squared was 9x squared, plus a squared, which is 17, divided by 2, times the sine inverse of u, which was 3x, over a. Well, I got a squared to be 17, so that makes a the square root of 17, plus c. And honestly, this is my solution. The only other thing I could possibly do to this guy is to distribute across each term if they happen to do that. And you can see this is kind of setting you up for multiple choice questions on tests and the like. But well, the only other thing I could do is literally multiply through by my constant. And if I did that, that would be negative 5 over 3 goes in 27 9 times. And 9 times 2 is 18. And notice a negative times a positive is a negative out front. Times the square root of 17 minus 9x squared plus, all right, and then we got to have 5 times 17. Grab the calculator here because I don't think any of this reduces. So 5 times 17 is 85 for 27 times 2, which is 54, times the sine inverse of 3x divided by the square root of 17 plus c, and here is your solution. And the offhand chance that they give you a function with bounds, instead of putting the plus c, you would put your bounds from a to b and use your fundamental theorem of calculus, plug in top minus plug in bottom. So again, what happens when you need to integrate really hard stuff that all the other techniques doesn't work? Well, always the tables in the back of the book are going to be the key to this stuff, because they're going to have lots of tables that are difficult to integrate. How tough can they make this particular stuff? Well, your teacher is going to go through this material and show you some interesting problems, but I decided to do one interesting kind of problem, and I went ahead and tried to give you a formula for this. But before you even look at the formula, this is the trick here. First off, before you even look at the formulas, identify the type of problem it is. Again, it looks like the square root of a squared minus u squared, because it's a constant minus a variable. And go ahead and identify. A squared's got to be 25. U squared is going to be e to the 2x. That makes a, when I take the square root of 25, I get 5. But that also makes u equal to, if u squared is e to the 2x, that's going to make u equal to e to the x. And let me explain. As u squared equals e to the 2x, you would take the square root of both sides. But when you take the square root, that would give you u equals the square root of e to the 2x. But a square root is the same thing as a half a power. And a power raised to another power you multiply, and 2x times a half is just x. And that's where I'm getting the e to the x from. But I want to remind you, this is u-substitution. Once you identify u, you got to do du. The derivative of e to the x is e to the x dx. So now let's substitute. And this one requires a little bit of a trick. I'll show you. This will be the integral of the square root of a squared minus e to the 2x is u squared. But now I need to substitute in for dx. du is equal to e to the x dx. So I'm going to move the e to the x. Even though it's a function, I can move functions to the other side too. So I get 1 over e to the x du equals dx. But when I'm substituting, I have nothing but u's. Who's e to the x? E to the x is the same thing as u. So this is 1 over u du equals dx. So I get to replace dx, but I get to replace it with 1 over u du. And so there's a classic little trick there that, you know, I'll let u equal something or other, but du is not in the problem, but you can move it to the other side and put it into the problem. Dx is 1 over u du. So I replace dx with 1 over u du. Now, we want to clean this up. So make this a fraction over 1, multiply numerators. This will be the square root of a squared minus u squared over u du when you clean it up. And this is the form that you'll be looking for, which I just so happen to pull it off the table for you guys. This is the square root of a squared minus u squared over u du, which is equal to the square root of a squared minus u squared minus a times the natural log of the absolute value of a plus the square root of a squared minus u squared all over u plus a. So I get to replace this guy with my formula, which is the square root of a squared minus u squared minus a natural log absolute value of a plus the square root of a squared plus u squared all over u, and a big old plus c there. Okay, now the last thing we're going to do is to back substitute. So this will be the square root of, and what was a squared? A squared was 25, minus u squared, which is e to the 2x, minus a was 5, times the natural log of the absolute value of a, which is 5, plus the square root of a squared, which is 25, minus, that should be a minus there, minus u squared, again copying it from my formula up here, minus u squared, which is e to the 2x, all over u, which is e to the x, close absolute value, plus c, and there's my solution. So again, identify the formula and then type in the table what it's equal to in the integral tables, and then back substitute. So this is a large part of u-substitution, but you have to worry about manipulating constants and sometimes manipulating functions on the du stuff as well. So this is probably the hardest type that you'll run across. So I hope this has been helpful, and I'll see you in the next video.